Hello, I'm Zhao Tong from Areas of Antibodies. Today, I'm going to present our work, Progressive Discrete Domains for Implicit Surface Reconstruction. In this work, we focus on one family of reconstruction methods, global implicit reconstruction methods. For example, the famous Poisson reconstruction and its variants, smooth sign distance reconstruction, Voronoi-based spectral reconstruction, sending the unsigned, etc. All of such methods follow the same schema. Given a point cloud with orient or unorient normal, we discretize the geometric domain on which we solve a global energy optimization problem, and then we extract the zero set of the obtained implicit function to get a triangle surface mesh. Although many different energies are proposed, the domain discretization step draws much few attention in literature. However, we'll show that it has a huge influence of the final reconstruction results. Here are the two common choices in literature. Octree used in Poisson and SSD, which is a hierarchical structure of cube nodes, and tetrahedralization used in spectral, sending unsigned, which is the unstructured union of tetrahedra. Octree discretization has several advantages. It is a regular hierarchical structure which allows using the multi-solver grade, multi-grade solver, which accelerates a lot the solver speed, and it is easy to compute, given a point cloud and the user-defined octree depth. However, it is axis aligned. When features is not aligned with octree edges, the reconstructed surface has more artifacts, and it is data-driven, which are not suitable for several cases. Here we show three failure cases caused by the discrete domain. The first is when point cloud contains big holes. In this point cloud, there's a big hole under the sculpture. That the region is not well refined by octree. After the reconstruction, the lower part is not smooth at all. In second case, we have only sample points along curvatures. Since a lot of parts we don't have input points, the final surface is very coarse and not smooth enough. In several solvers, for example SSD, sometimes we need a strong regularization. For example, in third one, we want to smooth a lot the sharp features. However, the final surface is sparse around the region where the high curvature exists, and some artifacts appear due to the bad discretization. Another common choice is tetrahedralization. The advantage is that it is not axis aligned, which means that it can be aligned to any local features, and it is easy to control by adding or removing vertices in the tetrahedralization. However, the shortcoming is that it is not regular, that bad-shaped elements introduce artifacts into the final isosurfaces, and it does not benefit from multi-grade solver, which makes it slower than methods based on octree. In literature, there are two principal choices to initialize the tetrahedralization. The first is to insert all input points into the triangulation and then do a Delaunay refinement. This method is simple, but when the point cloud is noisy or its density varies, it will introduce instability into the variational system and make the system fail. The second is to initialize an octree on the point cloud and insert all octree points into the triangulation. As a result, it suffers the same problem as octree discretization. So what is a good discrete domain for such methods? It should at least satisfy the following three properties. 1. Well-shaped volumetric elements are revealed to ensure good numerical conditioning for the solver. 2. Well-shaped elements of the output surface mesh. And 3. Just enough degrees of freedom near the reconstructed surface to reduce the computational cost. To meet all these requirements, we proposed a progressive cost-to-fine approach that jointly refines the implicit function and its representation domain. An optimizer is designed to provide well-shaped elements, and the refiner is designed to provide just enough degrees of freedom. The whole framework is shown in this figure. Given a point cloud, the domain boundary is initialized by a loose sphere bounding the input point samples, then refined by coarse linear refinement. The algorithm iterates through the solver, optimizer, and refiner. The idle surface contoured by matching tetrahedra is generated as output once user-specified criteria are met. So let's begin with the mesh optimizer. Given the linear triangulation with the implicit function solved by the solver, we relocate the triangulation vertices so as to improve the quality of the domain. It is achieved by minimizing three carefully designed quadratic energies. The first is the as similar as possible energy, which improves the quality of the volumetric elements. It deforms each tetrahedron T to make it as congruent as possible to an equilateral tetrahedron T prime under a scaling operator that preserves the volume and the centroid of T. The first step to find the best approximating rotation matrix between T and T prime were inspired by ASAP transformation. We begin from translating T to its centroid and then compute the covariance matrix between the translated T and T prime. We perform an SVD onto C. To decide the scaling parameter, we compute the ratio between the volume of T and the van of T prime, then modify the sigma, which is an isotope matrix. At the end, we compute the rotation matrix as star as the product of V, sigma, and U transpose. Using the matrix, we can define our ASAP energy. We minimize the difference between the current vertex coordinates of T and the rotated and scaled T prime. The variable to optimize is VTI, the vertex coordinates of T. Here we show empirically that the ASAP energy helps improving the solver conditioning. We initialize the geometric domain and choose SSD solver. We start by comparing the number of iterations to make the SSD solver attain a fixed tolerance error before and after a pure ASAP optimization. We observe that both the number of needed iterations to make the solver converge and the computation time decreases during the progress. We show as well the histogram of the hydro angle of all tetrahedra. The number of slivers also decreases. The second objective of the optimizer is to produce well-shaped elements for the idle surface. Here we show 4 triangulations for contouring a unit sphere. The implicit function is computed theoretically for each vertex. The triangulations are generated by 2 layers of either randomly generated or evenly placed vertices sampled onto concentric spheres. We show that the fourth triangulation, the one with unbiased and evenly placed vertices, produce the best idle surface, with most triangles of the idle surface well-shaped and uniformly sized. This motivates us to invent an energy which forces the idle surface passing through the midpoints of tetrahedra. This energy, we call it Midedge energy. It concerns all tetrahedra intersecting the current idle surface. For each edge intersecting idle surface of T, we forces the vector between the midpoint of this edge and the intersecting point between E and idle surface to be perpendicular to the normal of the idle surface inside T. The variables are VE1 and VE2 in this formula. Together with ASAP energy, it favors equilateral triangles with similar sizing. Here we show the efficiency of the optimization energies by comparing the following 4 setups. Non-optimized result, optimization with Midedge, optimization with Alliez, and optimization with both energies. We show the histogram of isosurface angles. We see clearly that the fall produces an isosurface with much higher quality. To prevent the boundary of the triangulation from expanding or shrinking during optimization, we add a damping term to restrict the movement of the vertices near the domain boundary. We at first define a linear interpolated weighting function, which is zero between the layer of tetrahedra intersecting isosurface and is 1 on the domain boundary. The damping energy is then defined by ED. A large GD indicates a strong constraint which prevents the moving of vertex V. The final energy is the weighted sum of the above 3 energies. The energies are carefully chosen to make it independent to the scaling of the input point cloud and the scaling of each element. Since it is quadratic, we minimize it by a linear solver of size 3 times the number of vertices in the triangulation. And here we show 2 examples before and after optimization. Now we can move to the mesh refiner. We propose 2 refinement schemas to subdivide triangle facets of the isosurface with variable granularity, which preserves at most the shapes of both the isofacets and the tetrahedra of the 3D triangulation. Notice that there are 2 configurations of tetrahedra intersecting isosurface. The first case refers to tetrahedra having 3 vertices with sin signs, and the second refers to the one having 2 positive vertices and 2 negative vertices. We'll treat them separately. The first schema is trisection refinement. For tetrahedra to be refined, we add the trisection points of each edge and the centroid of each face into the triangulation. For case 1, the refinement results in 9 isofacets inside the original tetrahedra. For case 2, the ratio is not always the same depending on the shape of the tetrahedra. It is between 9 and 17, with an average 12. The advantage of trisection refinement is that it preserves good properties of both the volumetric elements and the isosurfaces, but it can be very violent since we add too many points into the triangulation. The second schema is bisection refinement. For tetrahedra to be refined, we add the midpoint of each edge with same value signs. For both cases, the isosurface is divided into 4 triangles. The advantage of bisection refinement is that it inserts less vertices during one pass, providing just enough degree of freedom. But the resulting smooth tetrahedra are no longer isotope, thus need to be optimized in the following steps. We designed an adaptive mesh refiner based on the 2 strategies mentioned above. Given a tetrahedra of case 1 with current area T and target area T prime, we trisect it if the ratio between T prime and T is larger than 9. Between 4 and 9, we bisect the tetrahedra. Between 1 and 4, we bisect it with a certain probability. And if the ratio is smaller than 1, we don't refine it. For case 2, we follow the similar concept, but we replace the ratio of the trisection refinement by 12. Last problem to consider is how we define the target sizing of T. We propose 2 strategies. The simpler one is to define a uniform sizing field, which is straightforward. The other one is to provide a user-defined sizing field S. User can come with their own sizing fields, but we provide a reasonable choice guided by the curvature of the isosurface. Our sizing field is dense near the region with high curvatures and sparse otherwise. For more details, we refer the audience to our paper. We provided the implementations of 3 solvers, screen Poisson, SSD, and spectra. We use piecewise linear basis functions defined on each vertex of the triangulation. Note that our method can be generated to other solvers which are discretizable on tetrahedral meshes. The problems are solved then by either a standard linear system, which is the case for Poisson and SSD, or a standard general eigenvalue problem, which is the case for spectra. Here we show the progressive reconstruction process of the math point set. The optimizer and the refiner jointly improve the quality of the discretized domain and isosurface mesh. The discretized domain is getting denser and denser while sandwiching the reconstructed isosurface. The ratio between the number of vertices near the isosurface and of the entire triangulation increases rapidly, showing that we allocate more degrees of freedom where needed. We compare our results with the original octree-based SSD on model with increasing level of noises. We observe that they achieve almost the same regularity when the noise level is low, but when we increase sigma, the octree-based SSD becomes more and more sensitive to solver parameters, and the isosurface becomes less and less smooth. Note that for octree-based SSD, the parameters are carefully tuned to make the isosurface as smooth as possible with a good topology. Here is a laser scan with large holes and imperfect normal. We can see that due to the insufficient discretization around the big holes, the octree-based SSD introduces unexpected artifacts. Here is another laser scan with holes. These bumps with high curvature variations are in contradiction with what is expected from an SSD solution on smooth point cloud with strong Hessian penalization, indicating that the allocated structure prevented the solver to obtain an accurate result. We show in this figure the execution times of the models used in our paper. Each color corresponds to one loop of optimizer solver refiner, and the pink indicates the final solver. Compared to octree-based solvers, our algorithm takes more time. However, it is scaling fairly well with the number of input points, and the execution time almostly depends on the user-defined target setting field. What's more, it can be accelerated by some technical strategies, for example, using algebraic multigrid solvers. To conclude, we proposed a progressive domain approach for global implicit surface reconstruction methods. It iterates over three main steps: solver, optimizer, and mesh refiner. The output mesh is of high quality and is adapted to the intrinsic geometry of the point cloud. In the following, we would like to improve our approach from several perspectives. Firstly, we want to try more sophisticated mesh refinement methods or a combination of refinement and coarsening. We want to use higher order basis functions instead of piecewise linear functions. We would like to adapt our domain to sharp features in order to reconstruct them with no distortion. Although the classic solvers cannot deal with such situation, our progressive approach is capable of discovering sharp features and modifying locally the solver to make them appear. That's all for my presentation. Thanks for your attention.